Good evening, everybody. This is Ivan Čukić. You know me from previous C++ Russias. And tonight or today, depending on your time zone, I'm joined by the great Andrei Alexandrescu, who tries to destroy everything, and I think that most of the time he succeeds. I don't think that he needs further introductions. The only thing that I'm going to mention is that he invented the word modern in modern C++, which I think that everybody is abusing quite a few years after, after his book on modern C++ design came out. So, hi, Andrei.
Hello, and hello, everybody.
So the first question that I wanted to ask you is completely unrelated to your talk because I don't want to spoil anything. I heard that you used to drum. Does your man cave has a set of drums, or?
By the way, everybody, welcome to my man cave. We're in my basement here, where it's the only space in the house where I can choose my furniture. Otherwise, it's my wife who dictates everything. So, sadly, I don't drum anymore, but we have a grand piano. Like a big piano upstairs, and my kid is in the conservatory program, and he's a pretty good pianist by now, and I'm enjoying music through him mostly. I don't play much anymore.
That's unfortunate. I wanted to create a C++ band, not the one from CPPCon, you know.
That may be interesting. Yeah. We can talk about that.
Yeah. You're still in the US?
Yes, I'm in Boston.
I wanted to ask you because the last time that you were at CPP Russia, you worked at Facebook, and now I saw that you are self-employed. Is it you enjoying your work on the deprogramming language or something else?
Yes, quite a few things actually. My career has been marked, maybe kind of in a good and a bad way simultaneously, by very diverse interests. So I like to do, of course, C++. It has been sort of my first love in like anything related to programming. Then there's been I've done a lot of work in machine learning in my academic days. I've done work at Facebook. I've done research, also like machine learning and natural language. But also I've done a lot of just systems work. HHVM, the HHVM compiler, the Facebook PHP compiler, and a lot of optimizations on that. The Facebook has a Folly high performance library written in C++. I wrote quite a bit of that too. And during my all of this time, I've also had enjoyed working on the D language a lot, and that's been kind of a constant thing for me since like 2006. And right now, I'm actually working with two companies. I'm a dedicated father of two, so I need to bring income to the house and make sure that everybody has bread on the table. So I actually work with Bloomberg. And actually, this talk is derived from my work with Bloomberg that we're going to see today. And also with a hedge fund in London called Symmetry Investments. And that's a D shop. They only use the D language throughout. And it's a lot of fun. I mean, it's really nice. There's a lot of generic programming going on in there. There's a lot of like compile time stuff. And, it's an interesting place to work.
That's cool. I'm not going to take your time anymore from the presentation. I just want to say to all the audience that don't forget to ask questions. You're more than welcome. Just post them to Telegram or Telegram. And obviously, Andrei will indirectly answer them. I'll just pass on the questions to him. So, Andrei, I'm giving you the control of the mic and everything else.
Thank you very much, dear colleague. Okay, so we're going to discuss today a topic that I've also presented at my CPPCon talk just a month before this. And it has to do with variant types. But before that, I'm going to make a few remarks about you folks, C++ Russia and the Russian public in general. I've had a great time last time I visited, and I gave a talk at CPP, C++ Russia, and I got very nice feedback. There's also a talk at the .NET conference, kind of on the other side of the town, right? um, and it was a really nice trip. I enjoyed it immensely. But there's one piece of feedback that was interesting, and I'm going to try to act on it today, which was the following: many Russian people said they don't understand my accent. So they said, it's just like it's your standard European, Eastern European accent, but it's just different from the Russian accent. So I had difficulty kind of understanding it. So I'll try to speak, kind of to enunciate, to use the Queen's English, if you wish. Try to do my best with pronouncing the words clearly and as much as I can, because obviously it's not going to be anywhere close to Queen's English, right? Just wanted to say thank you very much for joining this talk today, and thank you very much for. I know it's 8 p.m. in Russia, and I assume there's quite a few of you in other places, but the majority should be kind of renouncing, giving up on their dinner time to attend this. So thank you very much. So we're going to talk about variance, and one important topic is why would this be an interesting topic? The topic is derived from an upcoming book by Bloomberg authors, Embracing Modern C++ Safely. It's available for pre-order on Amazon, and actually I just looked up, and there are ways you can ship to Russia from Amazon. And I'm sure there are any number of bookstores and vendors and solutions for Russian programs to get their books. So I highly recommend this book. Actually, I wrote the foreword for it, and it's an excellent book. I participated to it, and I ended up writing a whole chapter for it on Veridic templates. And Veridic templates happen to be an important point, an important mechanism for implementing, of course, variant types. So that's how it all kind of comes together. So this would be my work with Bloomberg. You're going to see here a few other talks that I'm referring, and they're kind of in order of what's the deal with Tuesday and Wednesday and whatever. These were the CPPCon talks. So if you CPPCon will publish soon their talks, and you're going to see these other talks as well as mine. But I assure you that this online talk is going to be way better than the talk I gave at CPPCon. And of course earlier, because you're seeing it right now, whereas the CPPCon talk is not yet available. It won't be for like a month. So highly recommended this book, and sponsor obligation. I gotta tell you this. I work with Bloomberg, as I said, and I like them, and they're hiring. I'm not sure what the remote situation is with Bloomberg. I do know there are quite a few Russian people working at Bloomberg. One of them is the book author is Rostislav Hlebnikov. So you're gonna find a nice community there. And as I also mentioned, there's another company I work with as a consultant, Symmetry Investments, and they actually they do have a remote working policy that I know very well because I participated in establishing it. And it's a company that uses the D language, which is awesome. But of course, you don't have like millions of D programs kind of just waiting to get a job offer. So they would be very happy with C++ programmers working, learning D and working in D. And actually, the funny thing about this company is they do have a bunch of programs working from Russia. I know a few personally, and they're having a good time. And speaking of which, I gotta say, remote work for me is like terrible. Like there's been like this. I've been working with these folks for months now, for over a year actually. It's been since May 2020, so it's been like a year and a half. And for me, it's every day is like it's like Groundhog Day. I'm not sure if you've seen the movie. It's that movie with the day that repeats itself over and over forever. So it's like Groundhog Day, because I wake up and I get coffee and I eat breakfast or whatever. So I get to work. And by the time I get to work, the people in London and in Moscow, they're already like fixing my bugs. Okay. So they're in the middle of a fire extinguishing process. So they're already kind of working hard in the middle of things. And it's like, oh man, why do you come so late and everything? So it's 2 p.m. there, right? So I'm coming and it's like, oh my God, there's so much work to do. Crazy. This is like so much stuff going on right now, and I'm late. The state of perpetually being late is killing me. So then, I kind of get to work and everything. So I'm starting to kind of fix bugs and whatever, like extinguish whatever fires there are to extinguish. And by the time I get in the mood of actually working, everybody goes to sleep because this is remote work with Europe for me, right? So I get in gear, ready to get some work done, and then everybody's like, "Oh yes, I'm gonna have a whiskey now and go to sleep, or a vodka, as it were, depending on where you are." And so I'm kind of left alone all afternoon, and I work alone. And the problem is, next day is the same thing. So anyway, so I'm sure if you work remotely, you know exactly what I'm talking about. So I highly recommend you take a look at these guys and Bloomberg as well. They are awesome, and I would recommend both as employers. So here's the plan for today. We're going to discuss first variadic templates, because they are an essential tool for implementing variance. So and then we're going to figure out, why do we care about this particular type variant. It has its own name. It's a vocabulary type. And why the heck do we care about variance? It's kind of an obscure thing to worry about, etc. So we're gonna discuss why actually we should care about this type, and why we should implement it efficiently, it turns out. And then we're going to discuss a bit about stud variant in particular, the standard offering of variance. And last but not least, which is kind of the meat of the talk, and we're going to discuss some code and have a bit of fun. We're going to discuss I just invented this name, the converse factory method pattern, which is the opposite of the factory method. In the factory method pattern, if you recall, we're constructing something that we don't know exactly the type during compilation. So you're constructing something like from a name, from like some data coming from networking or a file or whatever, deserialized data, and we construct an object. And that would be the factory method pattern. We construct something, we don't know exactly what. With variant destruction, it's a weird situation, because it's the exact opposite. You know what you're constructing, because when you initialize the variant or you assign it, you know exactly the type of the data that you put in it. That's totally fine. But when you destroy it, you forgot what you have in there. So it's this weird situation whereby you don't know exactly what you need to destroy, so you need to find which destructor to call, and this is what makes the problem interesting. Making it also fast is going to be quite the challenge. Great. So let's motivate first variadic templates in general. So there's been like, if you're, as old as I am, you've been like with C++ for a while, like C++ 03, C++ 98, and you know that, oh my goodness, like whenever I wanted to do something with several types in like a variable number of types, it was very difficult and it was very awkward. There's been a need for things like class function templates with arbitrary number of arguments. There's any number of functions that you want to just simply take variable number of arguments. And the classic example would be the print function. Printf would be the C function that is very fast, but it's extremely unsafe. And compilers actually are known to detect that you're calling printf and try to figure out what types you're printing there from the format string, but that only works when the format string is available during compilation, etc., etc. So we would like to have a better mechanism for defining these variadic functions. So there's a nice motivation that we get to define these algebraic types, tuple and variant. Now, algebraic is like kind of a pretentious term, but it does make sense because tuple is called in kind of in theory, in the theoretical terms. Tuple would be that thing where you put like an int and a string and a double, and you put them together, and that's your tuple. And that makes a lot of sense in math, in physics. So a lot of calculus uses tuples naturally in math. And in programming, tuple is called a product type because the total number of states in the tuple is the product of the total number of states of its elements. So if you think you have a tuple of int and double, the number of possible values of the tuple is all the possible values in int multiplied by all the possible values in a double. So that's why they're called a product type, because they can store the Cartesian product of the two sets of values, right? So that would be a tuple. We're not going to discuss tuple today. I'm just mentioning it to brag. With variant, it's called a sum type. Why is it called a sum type? Because actually you can store anything, not anything, but a closed set of types in a variant, but you can only store one at a time. So they're gonna share the same memory. So they're gonna be there can be only one active at a time because there's no room for more. If you want room for more, you use the tuple. So that's obviously the difference between the two. With a variant, it's called a sum type because the totality of states you can store in a variant is the sum of states of each type that is supported by the variant, and that kind of is nice because it gives us a nice mental model on what we can do and what we cannot do with these tuple and variant types. So it's important to mention that tuple and variant use a closed universe of types. So you can't have a tuple that contains like any number of types, infinite number of times, unbounded. And you cannot have a variant that contains an unbounded number of types. For tuple, that doesn't make even sense because you can't have a type that is infinitely large. But with variant, it does make sense to I want to store literally any type that is representable in a computer, and I want to store one of those in a value. And actually, there is a possibility to do so with the appropriate implementation, and that's actually called any. And I think it was Kevin Henney who proposed any for Boost, and it's been in Boost for a long time. So Boost any it's actually a bag for anything. You can put anything in it. There's no bounds. And it has been standardized, I think, in C++17. So you can actually have in C++17, you can have a std : any, and that's going to literally store any type you want. The drawback here and the trick is that you need to know the type that you're extracting, because any cannot, it can't do nice things as variant does, because variant knows the possibilities in there, but then it doesn't quite know. So it's a bit more inefficient. It's a bit more clunky to use. So it's a bit more difficult. So staying with variant for now, let's look at other motivational uses for variadics. You can consolidate a variety of calculations, allocations, and locking in these variadic functions. Consider a function that it's actually given in the book as an example. Consider a function concat, which concatenates a number of strings. So you give concat some std strings, you give it some individual characters, you give it some built-in C strings, like 7 of those or 17, any number you want, right? And that's a classical thing you want to do when you build like a web page, when you return some response string from a server. Like it has so many uses, right? So I want to concatenate a string from many fragments of strings that come as different types. So the nice thing about having a variadic function there, as opposed to, for example, using plus equal repeatedly for a string. So you have a string and you say string plus equal this and plus equal that and plus equal the other. The nice thing about concat is you can actually pre-compute the length of the final result, allocate it once, and then nicely deposit everything in it. So instead of allocating once every time you're going to resize the buffer underlying the string, you're going to allocate once and very efficiently actually deposit all of the content in the buffer. So concat as a variadic function is not only easier to use and nicer and simpler, but it's also it can also be a lot more efficient. The same I mentioned functions such as print already, and you can think of things like minimum, maximum. A lot of mathematical functions are naturally variadic, sum, etc. Now, another interesting use is forwarding. So a lot of times you have the situation whereby you want to call constructors, but you don't exactly know the arity of those constructors. So how do you write a function that receives arguments and inside calls a constructor passing those arguments? So how are you going to do that? Obviously, the answer is you need some mechanism to do variadic number of arguments, and then you're going to forward them to the constructor. And the process of doing so is well known as perfect forwarding, and the fact that it's variadic is a key component of that. So all that sounds good. So it's been done in the C++ standard under the guise of make unique, make shared, and place back in vector, and there's the number of in-place functions in standard containers. So I'm sure you know all about this stuff. More interestingly, and this has not been done yet, so this is the place where your creativity may bear fruit here. There's a number of functions in the STL that could greatly benefit. Actually, they can benefit in an algorithmic way, not a tricks way, not an optimizations way. They can benefit algorithmically from variadic arguments. Consider functions such as all of, any of, mismatch, equal, merge, set union, set intersection. All of these could gainfully be variadic and perform a lot better compared to their like repeated comparisons. So think of equal, the simplest case. It may happen often in machine learning tasks. You want to compare like three things. You want to make sure that three things are equal, three sequences, or more than three. Like maybe you have like 4 or 5. In the simplest case, you have three sequences that are can be very long, and you want to see are they equal. And the simplest way to do that is compare the first with the second, and if they're not equal, I'm done. But if they're equal, I'm going to compare one of them with the third, and then I decide that they're all three equal. But consider the following. It actually does happen. So you have a data set that's 1 million elements, and you have another data set that's 1 million elements, and you have a data set that is 200 elements. Right? So you see what I'm doing here. I'm going to compare two very long sequences, doing 1 million steps, and then after that, I'm going to figure out that the third is much shorter, and it's definitely not going to be equal. So with variadics, you can actually implement a variadic equal function that iterates the strings in lockstep as opposed to iterating them like crazy several times. And that would be a different algorithm. It's literally a different algorithm, and it can be a lot more efficient in certain cases. And of course, sometimes you don't know the length in advance, etc., etc. So you can use input iterators, etc. So all of these are interesting topics to look into. The same goes about all of, any of, like maybe you have all of. I want to decide that all of the sequence are satisfy some predicate or are equal or whatever. And instead of iterating the whole sequence, the first sequence and the whole second sequence and the etc., I'm going to iterate cleverly in lockstep. So variadic function calls should do something. They ought to do something different than chaining calls. And to be honest, you would need static for that, because you would actually need to do this vertical iteration that's going to move your iterators in the variadic list together, as opposed to moving just one and leaving the others in place. So static for would be, I predict, an interesting addition to C++ that would allow interesting variadic functions. Now, to understand variadics, I leave you to the documentation in the C++ standard. That was a joke. you can't understand variadics by reading the standards, because simply put, I've actually tried, and it's maybe 70 pages dedicated to variadics, but they're like in 70 distinct places in the standard. So they're not in the same place. They're not in one variadics, and I read this paragraph, read this section and I'm done. No, it's not like that. It's much more difficult than that. So you gotta like read it, in different ways. Sometimes you gotta hold it like upside down, and it works better. So it's really difficult to figure out from the standard how variadics work. The rules are difficult mostly by enumeration and fiat. When I say fiat, like think fiat money, like so be it, right? Fiat means like I'm just gonna say it's gonna work like this, and that's it. There's no explanation, then there's no justification for it, and there's no it doesn't derive from something. It's like a new rule that we just introduced in the game. And this is what happens with variadics. There's a lot of new rules introduced to the game. They, of course, interact with the rest of C++ in various ways. So I leave it to you to memorize what expansions are allowed and where expansions are allowed. You can't escape this, friends. I'm really sorry, you just can't escape this. You gotta sit down and read. There's a table, there's actually a collection of bullet points, and these are the expansions that are allowed, and this is where the expansions are allowed. These two elements I'm not going to insist on, because I can't do more than reading the standard for you here. But what I may be able to help is the deduction rules. So the deduction rules are interesting and weird and difficult, and you can use mnemonics, you can use techniques for improving on that. So the number one thing to understand about variadics is that these parameter packs in variadics, they are a distinct kind. And when I say kind, I'm going to use my knowledge of like 1% of Haskell, because Haskell does have kinds. So in Haskell, all types are a single kind. So there's one kind and all types are in the kind. And then you may have, in Haskell, there's like modules and whatever, and functors and whatnot. And some of them are functions that take you from one kind to another. Guess what? C++ has the same, because templates are really a different kind than types. They're not types. So the template is a different kind that is not a type, and it's actually like a function that takes its template arguments and gives you a type. So that would be a template struct or class, right? So in C++, there are only like one kind, because all types are in a kind. There would be a different way to categorize C++ types. Like, for example, all pointers are a kind. All arrays are a kind. All basic types are a kind, and so on. So, there is a classification like that, and there are 14 of these kinds in C++. But the funny thing is, these variadic parameter packs are a new kind. And that means nothing that you learn about nothing that you know about current C++ without variadics can help you with doing variadics. So this is kind of the bare truth. You gotta forget everything you learn and consider these things kind of a complete different beast that list obeys only rules that are particular to that kind. So I should add that say that adding new kinds in C++ is almost unprecedented. Like C++ only added one kind in all its history, and that's the template, nothing else. And now with C++ 11, a new kind has been added, which is parameter packs. So this is kind of a huge deal. It's a big deal, right? By the way, there is an operator that returns something without a kind, because C++, it had to be peculiar, right? So I'm not sure if anybody knows, there's an operator, actually there's two operators that return something without a kind. And because I can't kind of take questions from the audience right now, I'll tell you. And it's a great conversation starter. Like you can tell anyone, like you go to a party or whatever, and you have a martini and you say, nice shoes. Do you know there's an operator in C++ that has no kind? So the way this goes is if you use a pointer to an object and you use arrow star, and then you use a function name, a pointer to member to a function, So you have a pointer to object on the left. You have a pointer to member function of an object on the right. And in between, there's the operator that says arrow star, which is, the reference both the object and both the pointer to object and the pointer to the member function. That returns something that doesn't have a kind. You can't take the type of it. You can't store it anywhere. You can't do anything except put it in parentheses and call the function call against it. So it's kind of a dark corner of C++, it turns out. The same goes about dot star. So you have an object and you say dot star and point it to member function, then what you get, it doesn't have a kind. Just saying, you can actually mention this, as a quiz to your whenever you interview somebody at your company, just say, what's going on with that dot star? All right. So the second thing to understand about variadics is it's all about the dot dot dot. So actually, dot 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 is the only operator that you can apply to a parameter pack. Whenever you have dot 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 to the left of a name, it means I'm introducing this name as a pack. So the example would go simply template type name dot 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 T is class C. So the dot 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 appears just before the name introduced me. It means I'm introducing a pack. Otherwise, the dot 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 can only appear after something that looks like, and please bear with me for now, something that looks like a type or an expression. And in that case, it means please expand this thing. And these are the only things you can do with a parameter pack. There's literally nothing else you can do. Literally, there's not one other thing you can do. People try all the time, and I'm seeing it's kind of a frequent mistake. People try to store a pack somewhere, like put in a variable like auto copy equals pack, right? It doesn't work. They try to using x equals pack. That doesn't work, right? So nothing works that you're used to, and that's kind of that's kind of a big bummer, because it means you need to learn a whole new way of doing things, and everything you've learned in school is not applicable. So I'm going to allow myself to open a parenthesis here to just say this line belongs in the C++ standard. So it should be added. Type sequence is actually, it makes a pack into a type, and that's a type we know how to manipulate. So you know what to do with type sequence of int and float and double, but you have no idea what to do with a pack that contains int and float and double. So type sequence actually allows you to manipulate packs as if they were types. And of course, there will be like, integer sequence is a close relative of type sequence, because, integer sequence, you give it a type. Let me use my fancy thing. So integer sequence, you give it a type, and then you give it a list of values of that type. And of course, integer sequence is like the worst name ever invented in the history of naming for the C++ standard, because it's actually a value sequence, not an integer sequence, because as I'm showing it right now, it actually can contain doubles, and it can contain things like pointers to functions and enums and a variety of other things. So integer sequence has aged poorly, so to say. By the way, there is a thing in STDTR2 called DirectBase, which gives you the base classes of a class. So you give it a class name, and DirectBase is going to return you a list of the direct bases of that class. So it's in the standard, it's in TR2. Now, the thing is, you can't return packs because there's no way to store them. So you can't actually return a pack. What do they do? Well, guess what they do? They define this. And the name that they define it as is called __ reflection _ type list. And believe me, whenever I need to use in my code something that starts with __, I know that something is wrong with the universe. I hope you agree, right? So clearly there's a need for this, and clearly everybody's going to define their own, so better put in a standard. Now that you have this little bootstrap here, we should add a couple more lines, but not too many. I mean, I'm just half kidding. Because in order to manipulate these lists of types, you need a head structure, and the head is going to give you the first type in the sequence, and we do it simply by using a recursion, right? And then we have the standard trick, I'm sure you know about underscore T, all of these underscore T things in the standard, which simply make it easier for people to write. Instead of writing type name head T type, you just write head T of something and it gives you the head. So if you have any pack that is put in one of these type sequences, then you can say head against that type sequence and you get the first element. And guess what's the next thing that I want to add to the standard? That would be the tail. And why do I want this head and tail? Because Lisp has proven that you can do anything you want with data structures if you have three primitives. These three primitives are head, tail, and construct. Construct a new list from head and tail. So let's actually define tail as well, which looks very similar. So tail, given a type sequence of t and t's, is going to return the type sequence of t's. And I wrote here, because simply there's no way to express this without actually this type sequence. You can't say using type equals t's ... There's no way to do that. You can do head. So you can do head with a bare pack, because head is just, you just return the first type. But with tail, you cannot, by definition, you cannot do this crucial step here. Using type, give a pack a different name. So you cannot do this with a pack. You can do it with type sequence. So we have head, we have tail, and then we have const, which is give me the first element and give me an existing type sequence, and then I'm going to construct a new type sequence from those two. And once you have type sequence, you have head, you have tail, and you have const, we can use everything in the Lisp programming language to help us with manipulating these packs. So I'm going to close the parenthesis here. But I think this is an important point of this talk. Like, we really need these artifacts in the C++ standard. Continue with variadics. Essentially, there's a rule that doesn't exist in the C++ standard, but essentially can be derived from it. And the rule, I called it greedy matching, and it's in that book that I mentioned in the introduction. The rule of greedy matching says the following: once a template parameter pack started matching some specified, explicitly specified template argument, it's going to never stop. It's going to match everything following it. So you can't say, please match up to here. There's no way to stop matching. So once it starts matching, either it doesn't match at all or it matches everything that follows, right? So I'm talking about template parameter pack, not function parameter pack. So let me give you an example. So as a simple, obvious consequence, if you have a parameter after a template parameter pack, you can never make it explicit. It must be always deduced. And here's the example. You have a template. It takes a type name t. All good for now. It takes a pack t's, and it takes another type u following the pack. And by the greedy matching rule, it means you can never specify this explicitly. It must always be deduced. That means if I call f with 1 and 2, then I'm going to have t is going to match the first argument, t is going to match nothing, and u is going to eat this too. So there's a weird right to left matching, if you wish, because this is reduced to 0. It's imposed to be 0 by the greedy matching. Now I can say, I can specify a few things explicitly. I can say f given int and int. Int, the first int is going to definitely go here to t. So the first is in fixed position. The second is going to be this guy. And then u is deduced. And it's going to also be deduced as int from this last three here, right? If I have a more complicated case, let's int and double. Again, there's no way to specify u here. So int and double is going to be t's. So t's is going to go to int and double, and the last parameter u is going to be deduced as const char star. So essentially, there's no way, once you have a function that has something following a parameter pack in the template argument list, then definitely those folks are going to always be deduced. So that's actually a very easy way to remember this rule, which is if you have a template parameter after a pack, it can never be explicit. So it's always going to be deduced. By the way, so I actually sent this to a number of standards people, and the information is in the standard, but it's in like 5 distinct pages of the standard, none adjacent. So this is a kind of a simple, very simple, how do you call that, distillation, if you wish, of some complicated rules and consequences in the C++ standard. So I'm very happy that there's a simple, easy form to express this. So by the way, what does this do? It's kind of interesting because we have type name t's, but t is never present. It can never be deduced. So that means t is always going to have to be int. There's no other way it can ever be anything because there's no way to deduce it and there's no way to specify it. So that means this is useless here. So you can simply delete this and return int from puzzle and you're done. There's no other way to, there's no way to bind t to anything else but int, right? So the second rule that I'm going, and the last rule that I'm going to discuss today with template pack deduction is the rule of fair matching, which is in a way the converse of greedy matching. And it explains a number of weird things that variadic functions do. So here it goes. A function parameter pack that is not at the end of a function's parameter list can never have its corresponding type pack deduced. So it must always be explicit. So the way this works is, for example, in here, right? So I have this t's dot values, and I have some non-pack after following it. So that means t's must be always explicit. So if I call f of 1, this is going to be forced to be the empty set, the empty list. If I call f explicitly with the empty list, of course, there's going to be the same thing. This is going to be the empty list. If I call f with int and double, they're going to go to t's. If I call f with int and int, here the last line is in error because I'm not providing enough arguments to the function. I should give you 2 ints for t's and 1 more argument for t. And many people get confused by this this last error. Like, I thought I'm going to get like an int for t's and an int for t. No, it doesn't go that way. Int is going to be matched by the greedy rule, and then we're gonna have we're gonna have the fair matching, which is gonna require that t gets a seat as well. So this is kind of the interaction between the two rules, and there are any number of weird consequences. And there's any number of examples that are bizarre that one can discuss. For example, if you have a function with 2 variadics, that means use is always going to be deduced by greedy matching, and this is going to always be explicit. And that explains a number of difficult matching examples, because it looks like the matching goes right to left when in fact it's just a combination of these 2 rules. In this first case, I'm going to have this is going to be the empty list. In the first 2 cases, t, because it's always explicit. So t is always going to be the empty list, and u is going to be here an int, and here is going to be int and char star. Many people believe that if you call f of 1 or f1 of 1 and 2, those are going to go naturally to t's because it's the first thing appearing there, right? Actually, they go to use, and that's kind of that makes it weird. Anywho, oh, and this is like even more fun. This is a corner case from hell. You have two packs followed by a type here, and this type is going to always need a seed because by the rule of fair matching, right? So it's always need to be matched. So here we have the first call is going to be with both types 0, and the second call is going to be 1 is going to go weirdly to t, 2.5 is going to go to t. And this is kind of the most interesting case that I wanted to discuss because this is illegal. It's actually illegal code because by the combination of the rules, use is always going to be the empty pack. And the standard says if a pack is always going to match the empty pack, then that code is illegal. No diagnostic required, which means it's on you. So whenever you have a parameter pack And it just so happens that there's no way to set it to anything than the empty pack. That code is illegal. And the problem is all compilers accept this code and they're happy with it. They're going to match you to the empty pack, and there's nothing you can do about it. But the code is incorrect. So this kind of illustrates a bit of the complexity of the Verdict templates and the rules that govern them, because even the folks who created them got to a point where, well, this is P equals MP. We don't know how to solve this. We're not going to require a diagnostic here, friends. So it became some sort of a Turing completeness kind of thing. And I'm very excited to say it's on you to figure it out. Of course, practical advice that goes about Verdict templates is, avoid these kind of weird combinations of many verdicts and many kind of, it just complicates matters without actually much benefit to the user. So take this take this under consideration, right? So we're going to move to finally, in a way, to variant types. And why do we care? It turns out that variants are a very important topic. So we discussed this in the beginning. They're discriminated unions, some types, and can hold only one of a set of types, and not to be confused with stud any. We discussed all of this. And an example would be I have a variant that can hold a null pointer, a string, a double, some pointer to object, a bool, and a void star. And it turns out this is the variant type that is often used in JSON storage. So in JSON, you can have, it can be a Boolean, a double, a string, a complex object, which would be sort of a hash table, really another, a full-fledged object with fields, or null, right? So that would be my variant type for JSON. It turns out that it's not only JSON that could benefit from variants. It turns out that wherever you turn, you're going to find variants, sometimes used, what's the word, surreptitiously, kind of in a hidden way. You don't realize there are a lot of variants going on. But whenever you have interpretation and whenever you have data types, not data types, file types and that kind of stuff, you're going to have variants somewhere. For example, in database, colon in a database is really a variant because it can be a string, it can be a date. Like the database engine defines the set of possible types in a column, right? So it's going to say it can be a date, it can be a string, it can be a number, it can be this, can be that, and that's about it. We're done. It can be null, right? So you model that naturally in on the C++ side, on the client, on the client side of the database. You model that as a variant. For spreadsheets like Excel and Friends, right? Each cell would be a variant because it can hold like a number, a date, whatever. So it turns out that you have a database, you have spreadsheets, you have any other file format, protocol, data, anything that's data oriented is going to have dynamic choices of one type or another from a given set. A very classic and huge use of variants is interpreters. If you look at the implementation, or actually the definition of any interpreted language, such as Python, Perl, Lisp, PHP, you name it, like even Makefiles, like anything that is an interpreted language is going to have some variant type where it's their fundamental storage value type. And these can almost always be a set of a given universe of possibilities. So a variant interpreter is always going to be a variant. And if you look at the implementation of Python or PHP or whatever, you're going to see that the creators of these languages, the implementers of these languages, spend inordinate amount of times optimizing their variants. So it turns out the variants are quite big. In domain-specific values, the values are going to be also in domain-specific languages. Values are also going to be variant types. In compilers, you're going to often store expressions as variants because they can be like in integers or doubles or whatever. Some other compilers use polymorphism, but I suspect that in most compilers you're going to ever see they're going to use variants in some capacity for something or another. Herb's keynote at CPBCon this year, 2021, he mentioned variant 7 times, which is quite a record because he talks about really high-level stuff, but it turns out that variants are such an important high-level thing. So good implementation of variants is crucial to performance. I'm going to assert this. And it turns out that a good destructor implementation, because destructor is the most difficult function to implement in a variant, is crucial to performance. Now, let me back up my point about performance. I did this experiment on Facebook's PHP compiler, HHVM, a few years ago. And it turns out that simply changing the inlining decision on destructor, on the variant destructor, turns out is going to decrease the number of instructions because the inlining is going to do that for you always. But even though you execute fewer instructions, it turns out your CPU time is increased by anywhere between like 0.4 and 1.1%. You know, and that's the bottom line. Like that's the response time of the entire Facebook site. And that's kind of an interesting tidbit because number one, each 1% in performance on the Facebook site is millions of dollars annually. Why is that? Because you know, if you're slower, you consume more power for the same amount of work. And power, you know, I say power, it's like you multiply that by the scales of tens of thousands or hundreds of thousands of servers that that a large company uses, and then you're going to look at millions of dollars in electricity costs. But it's not only electricity; it's also provisioning because if you are slower, you need more computers to accommodate the same load. So if you need more computers, you pay more money. So it turns out we're talking about millions of dollars annually in these costs for every 1% in performance. It turns out if you get to more than like, let's say 2, 3, 5%, you're gonna start things like your users are not gonna be bored on the site. They're not gonna be there anymore. It turns out there's in direct proportion, people want to hang out on your site with the speed of the site. That's why Google is absolutely obsessed about telling you how fast your search return like this many records in these few seconds, right? Remember, like whenever you do a Google search, it's going to do that for you. I'm sure the folks at Yandex in Russia are facing similar challenges as well, and they're really obsessing as well about performance of time to user, right? The TTL. Now, so it turns out that a simple decision about inlining a destructor is going to affect times quite dramatically, the bottom line. Now, there's a kind of a bizarre thing here because even though I'm executing fewer instructions, I'm going to spend more time executing them, which is surprising, but it's not so if you think of the instruction cache effects. A destructor is big. If you inline it, the whole code, the entire code is going to be big whenever you destroy anything. So that means the whole application is going to be bigger, and it turns out significantly so, and it's going to put more pressure on the instruction cache whenever you use it. So that explains the dichotomy here between the CPU instructions and the actual CPU time used. Don't forget that in large applications, the instruction cache is going to be a key component of optimization. So small code in a large application is almost always better. All right, so discussing the layout just for a bit. We have a class variant, and it takes one or more types. There will be an implementation for 0 types, which has all kind of trivial implementations for functions and whatever methods. No problem. So we're going to focus on the case with 1 or more types. So in this case, I'm going to have simply an enum that's going to tell me what the maximum size is. And by the way, since C++17, you can call max with an initializer list, which means you can pass it any number of arguments. It's variadic in a way by means of this initializer list. They decided to not make it variadic because the backward compatibility pressure was too high, so they make it, I'm going to allow it to take one initializer list. That's fine. So I'm going to compile to call stdmax during compilation, which is remarkable. It's a const export function. to figure out what is the maximum size of all of my types here. And I'm going to use here the ... as an expansion device to expand into size of T2, T3, T4, whatever, all of the types in the list. And that makes it very easy to compute the maximum size. By the way, there's another size of which has the ... right here where my hand is here, you see. So if you put a ... here, that's going to be completely different. It's not going to give you the list of size of for each type. It's going to give you the number of types in the pack, which is kind of surprising to newcomers, but it's a thing, so it's just there. Don't forget, size of ... is not a size of anything. It's just the number of things in the pack. And then I'm going to use the famous operator alignas. Alignas is the cousin of Legolas from Lord of the Rings, right? I'm sure you remember. So alignas is telling you can align this particular piece of data at to satisfy the alignment requirements of a type. And here again, I'm going to use the ... to expand. And if you specify multiple aligners, then it's simply going to be the largest of all. So we just use this, and we're going to allocate a simple buffer characters of size. There are many ways in which you can do this, and people use templated unions and whatnot, and no problem. And then for discriminating, for figuring out what the designated type is, you're going to use a small unsigned integer. In this case, we use unsigned because that's sort of a general thing, but you can always optimize this. Maybe one single byte is in some cases it's better, it packs better. In some cases you need like a short, like 2 bytes and etc. So this is kind of a good area of optimizing layout. By the way, optimizing layout of data is something you would do good to spend on in applications that are that have sensitive performance requirements. So layout is kind of a good, is an interesting area to optimize. So that's my variant. Swapping these two, I didn't note they make much of a difference. It might be the case if these types are very, very large that it's better to put the unsigned before, because it's going to come the first. It's going to be the first thing in the cache line there. But that depends on a number of variables. So that would be my layout. And the implementation, it's going to have quite the usual suspects. It's going to have construction. It defines I forgot, like maybe 17 constructors. It has like a lot of constructors from anything you can imagine. Other variants with the same type, the values themselves, etc., etc. It has emplace, it has swap, it has comparison for equality and inequality. And it has a few querying function, like give me the index of the current type, and is it valueless by exception? And what that means is I'm trying to construct a variant, but it turns out that the constructors of the variant may throw exceptions. So then the constructor may have thrown an exception, and in this case, I have kind of a nonsense variant right now. And it turns out that you need to reserve a special value here in the active field here. The way the standard does it, it's -1 converted to unassigned. So it's there's a symbolic constant. So the symbolic constant is going to be set. The active member is going to be set to that constant whenever you have this exception being thrown. And you have some non-member function that query the variant, such as holds alternative. Does it hold this particular type, right? I want to visit, which is kind of an absolutely crazy member function that I suggest you take a look at. I looked over the implementation in GCC and MSVC. It's thousands of lines, because what really does is multiple dispatch. So visit is kind of a topic on its own, and what we're going to discuss here I'm sorry to kind of impinge on your dinner here, but what we're going to discuss here is a small part of visit. It's the same principles at work, but it's only a small part because it doesn't do the multiple part of multiple dispatch. Get me this and get if it's the right type, etc. Most of these are all of one at runtime. So the two interesting functions here that are not all of one, and we need to optimize them, are visit and the destructor. And if you do them naively, they're all then for the destructor and visit with one argument, or they could be n squared, that kind of a polynomial in n for visit with multiple parameters. So again, visit is kind of an interesting topic on its own, and it's kind of a good thing to discuss and think about. So just to exemplify the easy part, maybe I want to define the top level function get, and if it turns out that this integer is equal, this compile time integer is equal to the current index of the type stored in the variant, I'm going to return that thing. Otherwise, I'm going to throw bad variant access. So thank you very much. Auto reference. I don't need to kind of write anything complicated here. I just write auto reference and I get like the appropriate type. I'm taking a const variant. There's a version that takes a non-const variant, which is identical almost. And then if obviously if I is not the active type, I'm going to throw. Otherwise, I'm going to say, oh, give me the variant alternative type that corresponds to index I. So give me like the ith element in this this pack here. We're going to implement it next. And I'm going to do the casting of the data storage to that particular type pointer. And then we reference the pointer to get the reference. And that's how the story goes, right? Nothing up my sleeves here, nothing complicated. Let's look at the variant alternative implementation. It's also in the standard, so we don't need to implement it. I'm just giving it as an example, and it's a simple case of recursion. Variant alternative with n and some pack is going to return by default n-1 and the tail of the pack, but if it just matches 0, then it's going to give me the first type in the pack, and that's pretty much everything there is to it. It's a really simple case of meta programming. Now the hard part is we need to do search, and as I mentioned in the opening, the destruction is really obeying the converse factory pattern. So I need to destroy something that I don't know exactly what it is, and that's when I need to figure out how to do the search. And this is typical for whenever you use type erasure. Type erasure means you're forgetting compile time information, and you store something that does not have that type anymore, that information anymore. So when you destroy it, you need to kind of, oh, what was I doing here, right? And those of you who are familiar with shared pointer, they know that actually the destruction of shared pointer is its own story. So it's complicated. It uses like a virtual destructor in a patch class and everything. So it's kind of a story. And I can't recommend enough the talk by Stefan T. Lavave, better known as STL, on this very topic. And I forgot the name of the talk, but I'm sure if you Google for Stefan T. Lavave and CPPCon shared pointer, you're going to find the talk about all the tricks and all the solutions they use in shared pointer implementations. So let's discuss the destructor here. And the simplest, our baseline implementation is going to do a linear search, which means I'm going to look at each, at each type in sequence. And when I find the right index, I'm going to call the destructor. And here's how it goes. I'm going to implement a sort of a basic overload. This is my stopping the recursion thing that does nothing. And the interesting part goes in a template that takes the index, the current index being searched, the type, and this would be the pack. T and T is the kind of head and tail of the pack. Oops, sorry. And destroy linear takes also at runtime the integer to be searched. So this is this would be my current index that's at runtime, and I need to compare it with the index at compile time. So this is kind of the interesting part of this function. And I have the void pointer, which is my my raw data, my storage. So if n equals I, it means I found it. The search has been concluded, and I'm going to do the static cast because I know exactly the type and I know what the destructor to call. Otherwise, I'm going to recurse. And when I say recurse in these air quotes, it means I'm actually doing a compile time recursion, if you wish, because it's not the it's not the runtime recursion in the traditional sense. I'm not calling myself, but I'm calling a different template instantiation with I+1. I'm incrementing the value and the tail. And at some point, this is going to go away, and I'm going to call nothing, and that's going to be it. I'm going to call this first overload, which does nothing. So that's how the recursion stops. because I run out of pack. The types in the pack are kind of vanishing, right? So every time I'm calling destroy linear with fewer parameters in the pack. So that's fine. I want to make sure that deactive is less than size of dot 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 this. Remember, I mentioned size of dot 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 returns being the number of elements in the pack. So I'm putting this if here because remember there's that case in which variant was what's the name? Where is it? Valueless by exception. So valueless by exception means the index is kind of weird, like it's a weird large number unsigned. So I'm going to want to make sure that here I'm doing nothing if that variant is bonkers, right? If the variant is not bonkers, then I'm going to call the function, which is going to do the linear search and everything. So that's essentially my iterative version of destroying the variant. I'm looking for a match between the runtime actual index of the type and the compile time search variable, which I initialize with 0 here. So I'm going to search in sequence. So that's my linear destructor. And of course, whenever a programmer sees a linear search, they're going to think, how if I make it a binary search of sorts? I want log time and everything. So interestingly, parameter packs can be walked only linearly, but numbers can be halved quickly, both at compilation and runtime. So we got to do some weird combination of linear search during compilation and binary search at runtime, which is what we're going to do next. And it doesn't look that bad. It doesn't look that bad, but it looks different. It looks different from our usual kind of, I'm sure everybody in the audience has either written or looked at a binary search implementation, and it looks, if you squint, it looks like this, but it looks a bit different because there's a number of things you do during compilation, and there's other things you do at runtime, and this is what makes this function beautiful. So destroy log, I'm having my low and high and the pack, and I'm taking the runtime n. Now the question is, find n between low and high. This is sort of the challenge, right? Fine. So I can't do a loop because there's no way to loop during compilation with numbers. So I'm going to do a static assert here, making sure that my code has no bugs. And I also do an assert to make sure that my code has no bugs. So there's kind of a static precondition and a dynamic precondition here. And then I'm going to initialize this m as a const expert, meaning it's going to be computed during compilation. And yes, you can compute during compilation because both high and low, the search parameters are known during compilation. So that's good. And then I'm going to use the classical binary search 3-pronged test. Is it less? Is it greater? Is it equal? If it's equal, let's look at equal first because it's easiest. I found it, yay, right? So if I found it, then I'm going to fetch the variant alternative and I'm going to cast to it and destroy. So I'm done. This is like nice. If it's if n is less than half, then I'm going to go on the left side. And this test here is going to eliminate, save me a few useless instantiation of the template. So don't think too much about this. It's not important. But it's good to kind of reduce the number of crazy instantiations of this template because this template is going to instantiate a lot, as we're going to discuss in a minute. So destroy log of starting from low, going to the middle, and the parameter pack and everything. Otherwise, I'm going to look on the higher side, and I'm going to continue the search on the other side. And that's my logarithmic binary search destruction. And to call it, it's very similar to the one we had before. If deactive is less than the number of types in the pack, then destroy log, I'm starting with 0 and the number of types in the pack. These are my binary search limits, and all else is as expected. So that's my logarithmic destructor. It's going to do nice. Now, of course, whenever a programmer sees a linear search and then a log search, how about a table-based search, something that is constant time? And question for the audience, which I can't hear, is, but I'm sure many of you have in their mind already the answer, is given an index, a number, how can we call in constant time a function depending on that index? Wait a second, I remember there's a thing called like a table of function pointers that can give me exactly that. So a table would be a constant time solution for variance, for variant destruction. So constant time, there's no search. It's just you index into the table depending on the current index, and you know what function to call in constant time. So that's really nice. Excuse me. And it turns out that destroy element is simplest in this case, because destroy element would be I define it as a function here that takes a void star and a type t, and it simply does the casting and the destruction. And then I have this beautiful short two-liner really, which defines, depending on the packet, defines a table which is going to simply use expansion to plant the pointers to destroy element instantiated with the right type, boom, 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 and gonna have everything in one shot. I wrote one line of code and I created a table. How nice is that? Only Perl could do that, right? So essentially, I'm constructing my table in read-only memory. It's going to be static const, and actually it could be const export as well, because it's computed in compilation. It's simply a built-in compiled array of pointers to function, and then all I need to do is do the indexing. Here, actually, I made a mistake because I forgot to insert the test. If if the index is valid, then call the function. Otherwise, my program is going to crash really soon if I have a variant that's bonkers, right? All good. Now, question for the audience: which one would you use? Which one do you think is best? And actually, this one, the destroy constant time, it has a few things going against it, to be honest. The nice things going about it are constant time. It's small, it's simple, it's easy to understand. It doesn't have a lot of instantiations. However, indirect calls are going to be very slow, and I measured with both GCC and Clang that they just can't do anything interesting with that. Function is going to be really slow. And it's going to be wasteful for trivial destructors, which is often the case if you have like an int. You don't need to do anything when you destroy, but still you're going to have to go through that pointer to function that does nothing, which is kind of unpleasant. So the true solution to this this embarrassment of reaches, we have so many algorithms to choose from, but we don't know which would work best, is called algorithm selection. And it's actually exactly what you think it is, which is depending on the structure of my pack, depending on my variant instantiation, I'm going to decide using the linear or the logarithmic or the constant time. Because I can very nicely imagine that you may have a variant instantiation with 57 class types, which is actually in a compiler, it could happen because you may very easily have 57 AST type node types. So you may have a variant with 57 possible types, and then you're going to have to call a destructor quickly, right? And each has a destructor. They all have non-trivial destructors. So then this last solution, the constant time, may be actually very competitive. And then for medium size, whatever, you're gonna use the log search. And maybe for very short variant type lists, you don't bother with binary search. You simply do the linear search. So you can use algorithm selection depending on the structure of your parameter pack to decide which is the best algorithm for a case. So that takes us to toward the end of my talk. So finally, you're going to be able to have some dinner and a tea and whatnot, and enjoy the rest of your evening. But this, I'm going to leave you with this thought. We're ushering into a new era of C++, which is mixed mode algorithms. We have some algorithms that need to do some work during compilation and some other work during runtime, and then combine both. And this is new. This is like no language has faced this issue before, right? It's not in recent memory. There's no, we know the domain, and it's called partial computation. So there's papers on it, and it's kind of a whole field of computer science, partial evaluation. But in C++, it's kind of a peculiar way of partial evaluation, in which you need to decide very carefully what to evaluate during compilation, what to evaluate at runtime, and how to combine the two. And I think this is an interesting and new challenge on its own. And it's only going to you're going to only see more of it because there's more introspection coming in C++. There's going to be more compile time power. There's going to be more const export stuff in your life, right? And we're going to look at more of this stuff that we just discussed today. So I think that's this is very exciting. By the way, how many instantiations do we have for this logarithmic thing? Let's go back to it. So you're going to see that we have low and high and a pack. And we have these ifs here. These are runtime ifs. You can't do them during compilation because they involve this n here, which is a runtime number. So if you have an if at runtime, you're going to instantiate both branches. So the compiler requires that both branches are kind of compiled. So it's going to instantiate this guy and this guy and this guy, right? That means for each for destroy log with list of size whatever, I'm going to instantiate all combinations of low and high with low less than high. And that's actually n squared. So I'm going to instantiate a quadratic number of destroy log implementations for a list of n elements long. And that's a problem. Actually, the symmetry investments I was telling about this D shop earlier, in the D language is the same, the same problem. They're facing the same problems, and at some point, you have the issue you're running out of memory in on CI test machines because the compiler needs to instantiate these big templates, and these big templates occupy a lot of memory. So you need to find solutions to kind of compress the memory in template instantiation. So there's any number of solutions to that. And by the way, static for each is static for, which I mentioned in the opening of my talk, is a very good tool for avoiding these spurious instantiations. But sadly, static for is not in the does not exist in the C++ language. Getting back to my talk's conclusion, I would say that this is just the beginning. We're going to see more and more and more and more of this. There's going to be more mixed work in C++, and there's going to be more pressure on the memory during compilation and the compilation time. Already people are complaining about exponential time increases and compilation time increases whenever they try to do something interesting with templates. So we're going to usher into this new era whereby you need to optimize weirdly for compilation time, compilation memory consumed, and runtime performance, all at the same time. So that said, I do have breaking news following my talk at CPPCon. I got like 1 million requests from people, and it turns out that this topic is very appreciated by people, variance. And it turns out that, for example, Snap, they have their own variant type, was the makers of Snapchat. And I got I had a chat and got some emails from Eduardo Madrid. Thank you very much. And he works at Snap, and it turns out that Snap, of course, they have their own variant implementation because they care about the performance of the product. And they have an interesting switch with only 2 branches that expands in a Russian doll manner. Of course, you should know about this, right? Russian doll, right? So it turns out that Clang converts to a jump table, whereas GCC doesn't know how to. Let me show you the code. It's not complete, but it's actually very instructive because it's a switch with 2 branches, which is weird. Like, what the hell, right? It turns out that Clang detects the switch, this kind of a visit implementation, right? Remember the visit function. So it's a switch that only has 1 case and default, but it turns out that after Clang inlines this default case, which is a recursive call, right? You see, it's execute, right? It turns out that it's going to be in line into another switch. And that default in the other switch is going to be yet another switch. So it's going to be a Russian doll collection of switches. But Clang is going to flatten that whole thing into a big switch and is going to do a jump table. And actually, he showed me like Godbolt. He showed me the implementation in Godbolt, and it was amazingly small and fast. So that's quite impressive. So remember this kind of interesting use case of switch, which is switch with 2 branches, but the default is a recursion, which actually becomes its own switch after inlining. So, but then Andrei Petrushenko also sent me an email, and he found a really nice and simple solution that I like very much, but it requires C++20. So with C++20, you have these nice expansions of operators such as OR. And here, essentially, this is a linear search, which is done, if index is the same as the current integer in the integer sequence. Then I'm going to call the destructor and then comma true, just so it looks like an expression. And then or it's going to expand into as many or branches as the parameter pack. And the kind of the interesting tidbit about this is he uses integer sequence, which sort of automates this whole iteration process. So he simply initializes the integer sequence with the size of the number of types in the pack, and then it's going to iterate automatically from 0 to the number of elements. So that is pretty damn neat. And what is even more pretty damn neat is that he also sent me the godbolt of the implementation, and it turns out that Clang and GCC as well, so both compilers actually figure it out and implement a really, really fast solution depending on the number of types in the type list. So this kind of does in the compiler a lot of the optimizations we discussed that we do by hand. So that's quite impressive. And hat tip to both Andrei and the authors of these optimizers that figure it out from this this linear search expression. They figure out how to do actually a jump table and that kind of stuff, which is pretty impressive. So that's pretty awesome. To summarize, please understand these two rules that simplify our take on solving type deduction in function templates with variadic arguments. The rule of greedy matching and the rule of fair matching. Remember that variant destructors are difficult because fundamentally type erasure means you're renouncing some static information and you encode it as dynamic information. And get ready for mixed mode algorithms. I just made up this term, so it's partial evaluation applied to C++ templates. And please add that line to the standard. Contact your your local body your standard representative for Russia, or for exercise any influence you have to get that that simple line in the standard, because I think it's going to become very important going forward.